Future of database. Okay, it's always good to talk about the future. You can later look back at this lecture and you can see how many mistakes I made. Because the one thing about computer science is that we can pretty well guarantee that about every 5 years, lots of stuff changes. Now, it seems to me that we're right in the midst of some really massive changes. One of those is blockchain. We're going to talk just a little bit about this. We will have a lecture on how a blockchain is or isn't a database and what it's going on there. But that's a big one. But the other one is things like GPT-3 and artificial intelligence. And those are big, major changes that are going on. Between these two things, there's a massive amount of change that's going on. The third one that I think is really important is actually the Apple M1 processor. And you go, why do you think that's important in database? Because Amazon Web Services is planning on 256 core processors. And that is going to make a huge performance change. So I want to kind of touch on the things that are the big changes that are coming. And in the land of databases, distributed data is a big thing. And we have blockchain, which is one kind of distributed data. But when I talk about distributed data, I'm really talking about the stuff that's happening at Google with a database called F1. F1 uses as a front end the Postgres parser and language, so it is a version of Postgres of a sort, but Google in 14 data centers around the world put in atomic clocks to synchronize it. And these things are not cheap, but basically this F1 database, when it runs, allows them to have a NoSQL database at the bottom, a SQL database running on top of the blocks of the NoSQL database, but a worldwide data space, a global scale. That's what they call it. And it really is. I mean, we're talking about, it used to be 5 milliseconds. I think they've gotten it down to 1 millisecond latency database around the world. And that means that you can reliably send an email in Germany, okay, have somebody look at it a millisecond later in Tokyo, and you can be picking it up 3 milliseconds later because of the latency of light itself in the United States. And they will all be consistent and reliable. And that same database, basically, okay, is what is used for all of Google Docs and a slew of other things. Now, the question is, why did Google do this database? And if you go and read the F1 paper, Google, unlike a lot of folks, actually goes and pokes into their own code and figures things out. The reason they built an F1 SQL database is because they went and looked at their code and they found a whole bunch of NoSQL code that then in the application was doing stuff to deal with concurrency control. And the number of errors that they found in the concurrency control was more than on all the rest of the application in each one of these applications. And they went, you know what? It is better for us to ban NoSQL databases and build a single system that we can have that is a SQL database that has ACID compliance, that deals with the concurrency control once, where it may be a hard project to build, but you do it once and it's done. Okay? So this is available. You can get this through Google Compute and use it yourself for your own applications. It's, as you might expect, kind of pricey. It's not free. It is cheaper for you to, if you can do it at your scale, be able to install, a Postgres database on Linode on, say, 3 computers, 1 for a web server, 2 for a redundant backup between the computers. Will cost you a lot less than this. But if you need the kind of scale that this kind of thing provides, it is there, and it is available. And if you have that kind of scale, you probably have the kind of deep pockets where, $50,000 a month for your database isn't even going to make you jump. It's just going to be, oh, okay. So there is things like that, okay? I mentioned kind of NoSQL databases, but let's be more specific about the NoSQL stuff. I am a fan and not a fan of NoSQL. Again, it's a function of scale. If you have the kind of scale like Facebook with their Cassandra database, which is a column store, some people with large logging databases, Google with their stuff, NoSQL makes a lot of sense. In fact, it's critical infrastructure that isn't going to go away. If, on the other hand, you're storing a small amount of data, things like MongoDB don't make much sense to me. And I can stick MongoDB on a small computer and I can get it to run these days 5,000 to 7,000 transactions a second. These are documents. I can do the same thing with Postgres on the same computer and I can get 32,000. I'm talking about my laptop, 32,000 TPS with the same documents, with the same capability. So, this has been around a long time. It's optimized. It works. Let me give you an example of the kind of thing that you don't get in MongoDB. And this will help explain ACID compliance. ACID is a standard that was developed back in the 70s by a guy named Cobb, a researcher, about the serializability of data and guarantees about that serializability so that when you have committed something, you can guarantee that later if you came back and did it again, you'd get the same result. And basically it was done for financial systems. So a lot of things don't need ACID compliance. But a lot of things do. And it makes a lot of stuff easier if you just have it and use it. So what is it that Mongo guarantees? Mongo guarantees eventual consistency. And the reason that they do eventual consistency is you're not guaranteed that two different views that are replicated will actually see the same data at the same time. There's a lot of other guarantees you don't have. Like, you don't have a guarantee that when you've actually saved data to the database, that it's actually made it to permanent storage, okay, until, some point in the future. And you go, what do you mean made it to permanent storage? As been written to a disk. When you use Postgres goes through a lot of effort to make certain that stuff is actually written to the disk when it says it's committed. And it does this faster than Mongo. Now, most people don't realize this, but on Unix and Linux systems, every system call is interruptible. So you want to write a buffer of, say, 10K of data. And this stuff starts writing. 10K is way bigger than the disk block, so it's going to chunk off a piece, chunk off a piece, chunk off a piece, and right there you get an interrupt. And system calls come back and return to user land when this interrupt happens. Now, all of this data isn't written. And inside the kernel, it's just thrown away. It's not even kept around. It's gone. It just returns back to you, and it says to you, I wrote that much. Now, if you're very, very good at doing reliable systems on Unix, you catch this and you go, oh, I need to restart my write to write out this additional piece. Now, say you get another interrupt right here, and you've written 0 bytes. Lots of Unix code checks for 0 bytes being end of file. So you have to differentiate between, I have 0 bytes, but I still have work to do, as opposed to I have 0 bytes and I'm done. So you have to have some special code in there and restart it again. And this time it goes along and, oops, it gets another one. Now, these aren't this frequent. This is the deal, is, something's going on here while you're getting interrupts, okay, in the middle of a single write. Now, if you just write a regular user program, you might never see this happen. But if you want to write a database where you want to get consistency and you want this stuff to happen on a regular basis, reliably, then what you need to do is you need to deal with this. And you need to deal with this ugly detail about how it writes stuff. Now, Windows doesn't have this problem. It guarantees writes. It guarantees results. And you'd say, that makes it better. Well, it has its own set of problems. And one of the things I'm going to talk about is what the problems are in the land of Windows as opposed to Linux, Unix type problems. But collectively, okay, you've got Mongo, you've got things like Cassandra. Cassandra is from Facebook. A minimal implementation of Cassandra that makes any sense is at least 15 boxes. So this is not generally something people run in their home or in a lab. It is a big install. Microsoft uses a version of Cassandra that implements most of what MongoDB does so that you can have a shared, reliable, high-speed Mongo. But it's just different enough, just odd enough that you can't easily port back to Mongo. And they charge plenty of money for that. If you have a single developer using that kind of thing because of the minimum transactions per day type usage that's required, you're looking at that developer costing you somewhere around $600 a month just to use that Mongo emulator as opposed to use Mongo on their system. But of course, it's just different enough that if you want to develop for it, you have to develop for it, not for Mongo. So, yeah, there are other NoSQL databases. The most common one is some sort of hash store. And this is the ones that you find underneath Bitcoin and other databases like that. I'm just going to call it a database for the moment, even though it really isn't. But these hash stores, again, this is one of those ones that I kind of look at it and I go, let's look at the performance. The hash store that's used in Bitcoin, I can do the same thing in SQLite, all the convenience of installing using a file, and it runs about half the speed of SQLite. SQLite's been around a long time. They've figured out how to make it fast. The hash store doesn't have a command line interactive tool that I can use to poke into the data to make my life easy to pull stuff out when I'm testing, and it's half as fast. And you go, why would I use it? I have no earthly clue. But these things have become quite popular for a lot of people. They're right in the code, and you can just compile them in, and I guess they like them. Distributed databases. Probably one of the nicest ones in the land of distributed is a thing called CouchDB. CouchDB allows you to have detached subsets of data that you can update, and then it'll resynchronize automatically at the end, which for applications like you're building something out at a mining site and it's in a truck and the truck isn't always connected to the internet, something like CouchDB becomes a really nice tool for building a local copy of the database so things work while the person is out there, and having an accurate central copy of the database. So these are kind of the things that we see in a lot of databases. And what about hardware? I mean, I mentioned Apple's M1 processor. There are also dedicated hardware things for sorting. It turns out that about half of all CPU time spent on computers, not just your home computer, but about half of it is sorting. And there's an awful lot of sorting that goes on in databases. You're building an index to a table, it's sorting stuff. You're searching through stuff, it's sorting stuff. So having a hardware sort is kind of a big deal. And there are systems that either have hardware sorts, or there is a version of Postgres out there that uses GPU sorts that's very fast. And you can actually set that up easily on GPUs at Amazon Web Services. That's where I tested it and played with it. Setting it up, running a bunch of tests, doing some performance tests on that, cost me about $80. I think it was $81 in compute time to do that test, which, compared to the cost of a computer, and when you're getting a big thing with multiple GPUs, is really quite an economical thing to run a test. But hardware sorts in the land of database can be a really nice thing. Lots of performance gains. I would say that machine, based on my tests, you are looking at somewhere around 200,000 TPS machine. And that would be for about $2,000 a month. Okay, so yeah, that's a lot. I mean, 200,000 transactions per second. Not 200K. It's a little teeny K in there. 200,000 transactions per second for that kind of a price is, in my opinion, amazingly good. One of the things that is happening over time is that not only is hardware getting faster because we have more and more CPUs, more processors, solid-state storage for disks instead of rotating platforms, where the solid-state storage is 50 to 100 times faster. That's a big influence on databases. The operating systems themselves have gotten faster. The code inside Postgres has certainly been changed a lot to improve its performance. I can't say the same thing for Oracle. I can't see that it's had any performance improvements in a decade or more. But these things mean that we can build bigger, faster databases using existing technology. And performance is a big factor. It is, quite honestly, it determines a lot what you can and cannot do. So what other kinds of databases are out there? There has been, in the past few years, a plethora of these things. Like we have NoSQL databases. We also have network databases. And I find network databases to be rather an odd thing. When I first started doing database stuff in 91, okay, we considered for an application for a company I was working using a SQL database. Oh my goodness, that's complicated. Or a network database, which at the time seemed simpler. And before long, at that time period, people kind of decided network databases were basically a bad idea. Well, they've resurfaced, and we're seeing more network databases these days. In a certain sense, Cassandra, which is a column store, is also a kind of network database. But it's a sort of network database. But networks, okay, form a new thing in database these days that people seem to use. Time series. These are used for storage where you don't necessarily want persistent data forever, like log files. You might be interested in keeping in a database the past year's worth of log files, but the year before that, you just throw them away. And that kind of time series data turns out to be difficult to store in something like Postgres, as is, but the premier time series storage system is actually one that builds special indexes and has a series of extensions to Postgres. It is open source, and if you're looking for what I consider to be the highest performance, best time series database, it's built on top of Postgres. So those are kind of the things that you see out there in the future of a lot of database stuff. And the other one, we're going to do a homework on the small scale version of this, is text search. And the news in the land of database really these days is a thing called Elasticsearch. Elasticsearch is an open source, or should I say, was an open source database that just changed its license to something because they got tired of Amazon Web Services using their code and stealing their customers. And now it is GNU version 3 plus some extra clauses licensed in a fashion that will make Amazon unhappy, so Amazon forked the code base and they're going to do their own development on it. And other people that used Elasticsearch as their underlying database are going to do the same thing. Elasticsearch is the child downstream from a thing called Lucene, which is a text search system. So that's kind of the thing.